This part of the lecture is delivered on the topic small signal stability analysis in our system. Here we have the contents of the course which I will cover, uh, starting with the introduction on power oscillations, power system stability, how we can classify them, and next move on to small signal stability, how to perform it. So in fact, this lecture will discuss the fundamental of study on small signal stability of dynamic systems, as we can refer here from the topics which are included on this slide. And then how these studies can be performed, that will be illustrated with some examples. Yeah, it could be for on a small component or maybe for a large network. And next, we have the topics how we can represent the have the dynamic representation of the power system, how we can linearize them, and then a little bit more is detailed study on small signal stability analysis. And as I said that we will have some examples considered in discussion. So mainly refer to small signal analysis on components like automatic voltage regulator, and then a small system like a single machine panel bus system, and then we will have it for a larger network. So how we perform the small signal stability analysis for a large network? For this case, we have the examples of a 14 generator Australian power grid, and another one I wait for Nordic power grid. And to prepare this lecture, I mean the slides that I have in the lecture, the books by P.S. Kundur and Sauer Pai have been referred. And then some part of the publications or the work which was carried out in the Real Smart project, that is European Union Framework Program 7, and that has been as a reference in the preparation of these lecture slides. So next slide is the what we say it as the power oscillations. In fact, the power systems naturally they may have a few cycles of oscillations uh, being observed when we adjust to the new operating conditions, or maybe when they are perturbed, uh, maybe because of some disturbance as well. These oscillations, amplitude of oscillations, they can be of a smaller magnitude, and they can be of a smaller duration as well. However, the amplitude of these oscillations, they can become large, and there could be also, in some way, oscillations of sustained nature. And for this case, the control action will be required. So the power system operator will have the opportunity to respond to these oscillations, the response against these oscillations, and thereby eliminate the harmful oscillations, or minimize, or maybe the damp out these oscillations, right? Or maybe in fact which is less desirable, that is it may be with the use of relays to trip the lines or the systems or the elements. That is also another way how we can eliminate the harmful impact of these oscillations that may occur in the system. Now this slide shows how we can classify the power system stability. And as you can see here, the factors which had been used or represented for classification, it is on the basis of, let's say, some variable. And based on these variables, it could be as a rotor angle, frequency, and voltage stability. Next, these variables, these different types of stability or the forms of stability, they are subclassified according to the magnitude of disturbance for which they have been analyzed. And as such, you can have a small signal stability analysis, which could be for uh, duration 10 to 20 seconds. And another could be of a transient stability, which will last for much smaller duration, that will be 3 to 5 seconds. Then in respect to the frequency stability, we have it as a short-term of duration 10 to 30 seconds. And the next one for long-term, that will be of longer duration from 40 seconds to 3 minutes something. Now, in reference to the voltage stability, we have them as large disturbance voltage stability or small disturbance voltage stability. And in terms of time duration, they can be of few seconds to tens of minutes as well. Now, this classification of the stability, we have it referred from this source. So in this part of the lecture, our discussion will be concentrated, or mainly it will be on small signal stability for the system. And thus, we are much more concerned about the time duration of duration 10 to 20 seconds only. Now, what is the power system or the small signal stability analysis here? This is also sometimes referred as a small disturbance stability or steady state stability. Uh, This is how we classify here. That means as a ability of a power system to maintain synchronism when subjected to small amount of disturbance, and that could be of magnitude 5% around the initial operating point or the equilibrium point. So if the system is subjected to 5% of the disturbance around the initial operating point, then in that case, the analysis uh, will be referred as a small signal stability analysis here, right? And in this case, that as I said, that the disturbance is of much smaller magnitude, and as such, the governing equations which describes the uh, behavior, which describes the dynamic response of the power system, they can be linearized for the analysis purpose. That is the, we can say, the important feature that we have it for small signal stability analysis. That means the system is as a linearized form for the analysis here. In this case, we assume that the disturbance that causes the changes will disappear. It will not remain, or it will not sustained for a duration. Under the small signal disturbance, the power system is stable, and if the operating point returns to the original state, so that means under small disturbance, the power system will be stable if it returns to original state of equilibrium here. And such system, as I said, it is described by linearization of the power system here. We move to the next slide. Now, this slide we have how we can perform this stability analysis, more particularly I said small signal stability analysis. So mainly we have the dynamic power system model, because if you want to have the if you consider these several components which are integrated to each other in the power network, more or less they are non-linearly represented, and their response are much more dynamically behaved. But to perform the small signal stability analysis, we linearize them around the initial operating point. And with the linearization, we actually mean that we are able to obtain a differential, first order differential state variables, and which will be represented as a state space, you can say here. So the differential of the state, the first order differential state is equal to A into del X. And with this a matrix given, it is possible to determine the eigenvalues here. And then we can use MATLAB function EIG to compute the eigenvalue here. And this, as we can see here, that the eigenvalue is presented as a complex quantity, and thus it has the real component and it has the imaginary component here. So with this, it is possible to plot these eigenvalues in the S-plane, right? And then we have a real component along the x-axis and imaginary component along the y-axis on the S-plane. And with the location of eigenvalues on the left-hand side of the S-plane, it is expected that the response on being perturbed will have few oscillations, and it is likely to get settled down on the initial state here. And thus the response is stable here. However, if in case the location of the eigenvalues are on the right hand side of the S-plane, we observe that a time domain response, if I consider the variation of active power here, so it will be of increasing amplitude oscillations. Yes, and we can see that in this case, there is an exponential increase in amplitude of oscillations here. And thus, the system will be of unstable nature here. Now, what about the case when we have the eigenvalues located on imaginary axis over here? I mean, so with this situation, we are likely to have oscillations, right? We are likely to have oscillations of constant amplitude, and it will be of sustained oscillations. Yeah. Now for these two situations where we have an exponential increasing amplitude or maybe the sustained oscillations, the question should arise. Is it possible that we are able to stabilize the response of the system for these two situations? So that means can we have some way of compensation or the controller design such that these eigenvalues, they are shifted to the left hand side, and we are able to achieve a uh, stable response as which is shown over here. We move to the next slide now. Now, here, this slide is for discussion about the dynamic representation of the power system. As I said in one of the slides, earlier that the power system components, it will include the generators, the turbines, then the associated controls in the generator, maybe the AVR, automatic voltage regulators, then you have governors, and then you have the transformer, the line impedances, and then loads. This could be as a static load or the dynamic load, being represented by large induction motors. Now, thus the power system components, including the network, they are as a highly nonlinear behavior. Now, for the stability analysis purpose, we need to consider the dynamic response of these systems, and which can be described by some differential equations. So it can be by a set of n first order nonlinear ordinary differential equation of the form. Yeah. So that means we can have several number of states here, which will be the first order state here, which will be defining the nonlinear behavior of the generators. Then it could be for exciters. Then it could, that means the excitation system, or it may be for the governors, and so on. So this could be as a nonlinear function of some state variables of the components, and then also it will be a function of nonlinear functions of some input variables here, and that could be up to n order of the system here. And thus here xi represents the state variables, r represents the number of input variables, and thus xi here dot is actually the state's variable time derivative here, dxi by dt, it is referred here. Now in vector form, we can represent them as by equation 2, where you have the state vector given as a vector of state variables. Then you have a vector u control vector of input control signals. So you have even u2 ur, and then you also have a vector of some nonlinear functions which will relate the input variables and the state variables to its time derivative here. Now, the state of the system which we have, that represents the minimum amount of information about the system, which will be essential to describe its future behavior without any reference input at time t naught. Now, these state variables, they can be as a set of minimum number of dynamic variables along with the input variables to provide the system behavior. So thus you may have some number of state variables here, minimum number of state variables along with the static quantities and with the input quantities here, so that the system dynamic can be represented accurately here. We move to the next slide. We continue. So from the previous equation 2, t is the time here. Now, if I say that xi dot is not a explicit functions of time, that we can say as if the xi variable dot is only a function of the state variables and the input signals, rather than having a time quantity in the function, in the equation I mean. So thus the equation 2 we can modify here, and now this equation 3 is being referred as time invariant here. So you have the state equations being represented as a function of state quantity and input quantity only. Next, it is possible to have the output signals from the dynamic power system, and that can be represented in terms of input signals and state variables in the form equation 4, where you have the column vector, which will be actually a vector of m output variables. And then you have a vector of nonlinear functions, which will be m nonlinear functions, which will relate the input signal and the output state variables here. Move to the next slide now. So if I take this example here, so we have in the example shown, in the figure shown, a boiler, and then you can see that the boiler will have from the boiler you have the steam inlet through the system, and thus the steam input to the turbine, it is being regulated by the valve, and this turbine is coupled mechanically coupled to the shaft of the generator here. And then this generator terminal is connected to the bus, and let us consider you have a local load, and then also you have also connection to a line here. And then the generator has the field excitation. So what you observe that you may have the disturbance on the load side, you may have a step change in the load, step increase in the load, you may have this line being tripped, and that may cause a change in the electrical power on the generator side. Subsequently, if there is any disturbance on the generator side here, so there has to be also a change uh, regulated uh, from the boiler side or to the turbine side here, so that we can regulate the amount of steam inlet to the turbine. Now for this system as shown, you have the some input vectors, input variables. You may have some state variables which will define the dynamic behavior of the system here, which will be as a state vector, internal state vector. And then you may have some vector of output variables here as such, right? So with this example, we move to the next slide. So here I have example saying that let us consider that you want to model the silent pole machine which has the 5 windings, and we consider the internal voltage behind the subtransient reactance here, right? And then we can write down the first order differential equation of the state variables as some function f, which will have x state variable, and then there are some more state equations, state terms here, like ED, EQ, EFD. These are the voltages, quantities, and then the turbine power here, where the state x is again a vector which will have the state quantities from the silent pole synchronous machine in terms of the flux, which will be the main field flux along the d axis, and then for the damper windings axis, and so on. And then also a state variable related to the angular frequency and the rotor angle here. Now with this we can write down the equations also in other form as where we have x, and in this case we have the x represented, x state vector represented in terms of the current variable rather than the flux variable here. So we have it in terms of current. So in any form, we can represent the dynamic states of the synchronous machine for the analysis here. As we move to the next slide now, so now from the equation 3, it is actually a zero vector. If equation 3 is equal to the zero vector, so it means that the system is at rest, right? And then all the variables are constant and they are not time varying. Yeah. So now let us say that we can have these equations being represented as in this form now by equation 5. So we have the state equations which is around the initial operating point here, and that is equal to zero vector here. So that means the system is at rest here. But let us say that there is some disturbance and we want to linearize it, and how we should linearize it. So we perturb the system by some delta change. So delta change to the state variable x around the initial point. So we have a net change, new state variable x, which will be actually initial state plus delta change here. So that is the small deviation you have in the state variable and as well as the input variable here. And then the equation, the differential equations, we can write in this form here, where the nonlinear function, which will be actually a function of a state, the new state quantity and the input quantity can be referred here. However, this equation 3, 7, in fact, it must satisfy the equation 3 as well. Now, in fact, the equation 5, which we have it here, it indicates the equilibrium point basically. And equilibrium points, you can say, as those points for which the derivatives, as I said, it is non-varying with time. So that means those points for which the derivatives are simultaneously zero. Thus, it can be said that the system is at rest and all the variables are constant and non-time varying here. Now, if you refer to the equation 6, this delta change which we have, it refers to the small delta change, a small deviation. And then with this small deviation, that is small perturbations, this nonlinear function uh, can be expressed in terms of Taylor series expansion here. And then those, however, these second order and then higher order terms out of the Taylor series expansion, that we can neglect. And then we can write down equations as 8 and 9 here. So we had the with the second and the higher terms being neglected out of the Taylor series expansion, and then we have it as for one of the single state variable, we have written it here. So it is the partial differentiation of the function with state variable x1, and similarly we have it for other for nonlinear functions up to state n. Similarly, it will correspond to the first input variable to R input variable here. We move to the next slide. Now, from the previous slide, the question 5, we said that it must be satisfied. So that means we say that the variables, they are constant here and they are not time varying. So with these assumptions, if we can write equation 9 in the form of 10, so we have it in this way. Now, as shown in this figure, we have fx, that is the nonlinear function of some state variable on the y-axis, and the state, it is on x-axis here. Now, as you can see here, that this nonlinear function will be a sum of some particular characteristic, some particular curve nature, you can see here, which will be a function of the state variable x here. Now, as shown, if I consider that this is the initial point of the state variable x0, so thus the function will be nonlinear function, or equation will be a function of state x0 here. And if there is some disturbance, right, so how the function will move about. Now, if you refer from the equation 10, it is actually expressed as a time derivative, right? Equation 10 expresses time derivative for one of the n state variable here, right? And its linear relation to the state variables, remaining state variables and input signals here. deviation from the equilibrium point. So if there is this is the initial operating point, and if there is some perturbation of a small nature, small magnitude, right, either on this side or if it is on this side. So as such, here the system dynamic representation can be linearized here. So this is a linear region that we can do have. Similarly, if there is some amount of perturbations for which the point shifts to this one or it shifts to this one. So even for these situations, the behavior can be linearized around the point here. That is possible. Thus, it will be as a linear region here up to this range. But if in case due to perturbations, let's say the state variable, move somewhere here. So if you have the change in the state variable x01, it is somewhere here. So for this point, because we have a disturbance, and for this point of operation, the system dynamic response cannot be linearized. And that's why it is said, what about this region? So if the state variable moves to the point where the equations cannot be linearized. So in fact, we can have better linear approximation for smaller deviations here around the initial operating point. But if the deviation is large, because of large magnitude, then in that case, the equations cannot be linearized. And we need to consider the nonlinear response or the nonlinear representation for the dynamic systems here, rather than linearizing around the initial operating point. Right? So we move to the next slide. And now from the previous equation 10, we can have it represented in the form of a matrix as equation 11. So we have it as delta x dot is equal to A delta x plus B delta U, and where we have the matrix A as a Jacobian matrix of a function. So we have a partial differentiation of f1 with x1 and so on. And then similarly, we have the B matrix, which is again a partial differentiation of the function with respect to the input variables here. We move to the next slide now. Now from equation 4 with equation 6 applied, we can now write y is equal to, similarly, there we have discussed about the delta change for the state variable and the input quantity, and now here we have the delta change applied on the output variable. So we have it here by equation 12, and then we can write the equation 4 as by equation 13. So where here again it is a nonlinear function which will be of a function of state variable, new state variable, and new input variable here. Now with one single output signal, if we consider yj, let's then equation 13 again using the Taylor series expansion and then omitting the higher second and the higher order terms, we can write it as a equation for one of the state variable for one output variable. We can write it as 14 here. And then we have it finally writing down the equation as 15 for writing j is equal to for number of output variables m. We have it here. So we move to the next slide now. And next we are writing down the previous equation 15 in the matrix form as delta y is equal to c into delta x plus d into delta u, and where we have the C matrix which will be a partial differentiation of g nonlinear function with the state variables, and then D matrix, partial representation of the G nonlinear function with input variables. So with these matrices, which was in the previous slide, equation 11, and then next we have it in equation 16. This we can determine at equilibrium point, right, for which we want to analyze the system behavior against the small perturbations here. And thus the dynamic power system, when we write it in terms of perturbed quantities, so we have it written in terms of delta exchange, because we have considered that when the states are being perturbed by a small quantity, and thus with the input to state to vectors, we have it represented for the system for small deviations with the input vector delta u and output vector delta y. And this is how we can represent it as the as a linearized form here. Now from the questions 11 and 16, we have it system response, system dynamic in form of a static as a matrix form here. Then we can also obtain the Laplace transform from these state equations so that we are able to analyze in the frequency domain. And thus we have with the Laplace as transform. So we have it writing down. So thus delta x as a Laplace representation. We have it by equation 18 here. Now, in this equation, what we have it here, the delta x with the s Laplace as this one. And then ADJ refers to the adjugate and DT refers to the determinant here. And thus the determinant of A minus lambda I is equal to 0. That is basically the characteristic equation of a matrix A. So from here we can get the poles of the dynamic system, which will be the roots of the characteristic equation here. Now the values of S which satisfy this characteristic equation is also is deferred as eigenvalues of the matrix A here. So these eigenvalues can be either real or maybe the complex. And if matrix A is a real complex, then eigenvalues will always occur in conjugate pairs here. So thus, as I said, we have the poles of delta axis. This will be actually correspond to the eigenvalues of the matrix A, that is lambda 1 up to lambda n, that is the order of the system. All right. Now here we want to discuss how we can perform the analysis referred to the small signal stability. So eigenvalues of the matrix, they are given by the values of scalar parameter lambda such that the equation 1 is satisfied here. So A matrix A times phi I is equal to lambda I times phi I for I is equal to 1 to n. So that is satisfied. And then for any lambda I, the n column vector which satisfy the equation 1 is referred as right eigenvector of A associated with that particular eigenvalue. So it means that this phi A is actually as a vector represented as phi 1i, phi 2, 1, or phi ni here, right? And in fact, it has to be I here, phi 2i up to nth order, so ni here. Similarly, for n row vector, we'd have another factor satisfying the equation 3 as in this one. And then again for I is equal to an order, then is called term, this factor is called the satisfying the equation 3 is called the left eigenvector associated with that particular eigenvalue here. So we move next. So now if here we discuss some properties of these eigenvectors. So if left eigenvector and the right eigenvector, they correspond to different eigenvalues. That is, let's say lambda I and lambda j. So you have it for left eigenvector and right eigenvector for different eigenvalues. Then in that case, the property phi psi I j for one, that is lambda that corresponds to the lambda j, and phi I that corresponds to the lambda I eigenvalue. So that means if I not equal to j, so this property will always hold here. That means the product of the left eigenvector and the right eigenvector correspond to different eigenvalues. That will be always 0. Now, if eigenvectors are normalized, then equation 5 will hold for the same eigenvalues. So that means the product of left eigenvector and right eigenvector will be unity if they correspond to the same eigenvalue after normalization. And thus equation 6 will hold, that is as this one. And so since eigenvectors they are determined only to within the scalar multiplier, so vectors here we can normalize actually, and thus equation 5 and 6 will satisfy. Next we have the another property, that is the which is again related to the small signal stability analysis, and it is the modal matrices. Now introducing following matrices, that is equation 7. So we have it represented phi I is equal to as a vector here. Then previous equation 1, what we had it here, this one. So we can write down as this way. So we have it this factor, which is actually nothing but the diagonal representation of the eigenvalues of the matrix A actually. Then from 8 we can write in this way. So here we have if A has a distinct eigenvalues, so this term will always satisfy this relationship here. Now columns of phi, they are actually the right eigenvectors, and thus phi I to A with diagonal elements of the diagonal matrix phi factor having eigenvalues lambda I here. Right, so this is for column vectors. And similarly, if we refer to the row vectors and row vectors psi I, then equation from 3, if you go back, this one, which corresponds to the right left eigenvector, then we can have it as represented by this term, so satisfying the equation 3. So we have it as psi equal to psi 1 transpose psi 2 transpose, that is given by equation 10 here. Now next with these properties we want to discuss how we will be able to analyze the system response. And with this we consider a topic that is property related to free motion. Now for a system which is given by equation 11 here, that is actually the rate of change of each state variable here, rate of change of each state variable, which will be actually a linear combination of several associated state variables. So there would be a cross coupling between the states as such. Now, so here we say that the linearized system without forcing function. So we say that there is no input signal here. So thus, because of the cross coupling between the state associated state variables, we want to decouple the state variables, and so we introduce another state variable quantity, that is z here. And then we write down equation as 12. So delta x equal to 5 times z here. Now this equation 212, which we have it here, it is mainly written to decouple the state equations here. Now phi is the modal matrix of A, which is defined by equation 8 from the previous slide. Then if you refer to the equation 13, that is actually the you can say n decoupled first order equations here, because we have it as a z dot. So this will be the n number of decoupled state equations here. So that will be the n decoupled first order equations as in this form here. Then from equation using equation 9 from the previous slide, if you go back here, this one, right? So we can have modified, and thus we write it in terms of 14. So again, equation 14, it is a first order differential equation, as you can see, and it represents its solution here. Okay. And then from equation 12, we can write down in terms of response, time domain response of the state vector, original state vector. So this equation 12 has been modified, and then we have written it as equation number 15 here. So from those equations 14 and 15, we can further modify to equation 16 here, and then we can have it written in terms of equation 17, and thus this this is the you can say the z naught initial one, so it will be the magnitude of excitation of the ith mode here. So from these equations 16 and 18, what we have written as 19, so this is actually delta xt here in time domain as summation of phi I, and this term which is actually the linear free response for the initial conditions, it is now represented by Ci. So thus the question 19, it is actually a linear combination of n dynamic modes here. So with this discussion on the properties of the eigenvalues, eigenvectors, it could be left eigenvectors or the right eigenvectors, and then modal analysis for the free motion. We move further how these properties could be useful for analysis in respect to the power system behavior, in power system domain, I mean. So thus, with these slides, we want to discuss what is the importance of the right eigenvector. And as shown on this slide, with the right eigenvector, we can know what is the mode shape. We'll discuss about the mode shape in the later slide. So from the previous relationships, we had it delta xt. So we had it written in terms of these terms here. Now these variables, delta x1 or delta x2 or delta xn, these are actually the original state variables, right? And they represent the dynamic response of the system. And then we have introduced another state variables, z, which are actually the decoupled state variables. They are the transform state variables. And and they are of decoupled nature, and thus each being associated to only one mode, right? And thus these state variables, they are directly related to the particular mode here. Now the right eigenvector gives the mode shape. Uh, it means it is actually the relative activity of the original state variable when a particular mode is excited. So if I have to represent this phi as a matrix here, so you had it x1, x2, x3, and x4 as a row here, and then you have the eigenvalues. Sorry, you have the eigenvalues lambda 1, lambda 2, lambda 3, lambda 4 as column vectors. So if I consider the element of the matrix phi, that is phi 1 1 or maybe phi 2 1. So let us consider this one phi 3 2 here. So this phi 3 2 element of the matrix phi, it is actually corresponds to the state variable 3 and to the mode lambda 2 here. So that means it is actually the kth element. If I say the kth element here of lambda I here, right? So let us then in that case, I will have it as phi ki here. So let us, that means this is k is 3 and I, let us say mode is 2. So I is 2 here. So that means phi 3 2. So this is actually this term, this element phi 3 2. It measures the activity of state variable x3 xk to the mode lambda 2, to the ith mode here. So the right eigenvector gives you information about the activity of a particular state on a given mode, right? Similarly, if I take let's say 544, so here you go. So it will give you the activity of state variable x4 on the mode lambda 4 here. And these quantities which we have it here, they are actually as polar representation, polar quantities here. So they have the amplitude and they are associated with particular angle here. So with this, as we move to the next slide, so thus the next, if we have the left eigenvector, that is phi I, that gives the mode composition, and it describes about the weight composition of the original state variable uh, for the particular given mode here. So if I say that kth element of psi, so that means it will be as of particular mode psi ik, it will weigh the contribution of a xk state activity to the ith mode here, right? So thus the left and the right eigenvectors, they are in different form as such, you can say. So in summary, we can say that the right eigenvector, that is phi ik, it measures the activity of the state variable xk in the ith mode. However, psi ik, it will weigh the contribution of the state activity, contribution of sk's activity into the ith mode here, right? So we move to the next slide now. So from the previous equations, 17 and 19, we can write down as equation 17 here. In fact, 17, 19, yes, we have written it as 17. So this one, and in fact, I have rewritten these equations 17 and 19 here on this slide. So we get it ZIT as 5 items here, and we write down further as in this form. So what does this mean? So what we have it here, actually it is the summation of from k equal to 1 to n. So psi I k to phi ki. So that means it is actually the product of the vectors, right eigenvectors and the left eigenvectors. All right, and this will be unity. So that means the sum of for sum of all participation factors associated to a given eigenvalue will be always unity. We will discuss about this property when we take some examples in the later discussion. So, right now, what is this participation factor? In fact, from the previous slide, when we recall, it is given as pki, so that is psi I k to phi ki. It measures the relative participation of kth state variable, all right, kth state variable in the ith mode. So that means relative participation of a particular state variable to the mode. And how we achieve it? Multiplication of elements of the right and the left eigenvector, that gives you participation factor here by pki, which is again which is a dimensionless number, and it is invariant under changes of scale on the variables, and then constant ci that depends on initial conditions here. So I take the example to illustrate how we determine the participation factor here. So we have the right eigenvector, right, which is actually a column vector, you can see. So you have this matrix. So let us say phi 1 with the elements as phi 1 1, phi 2 1, phi 3 1, phi 4 1, because this will correspond to, on this side you have the state variable. If you refer to the previous slide, you have it here. This one, right? So you had it state variable, and this you have it as a column eigenvalues. So with this, you have it state quantities as row vectors, and then you have a phi 1 for each of the lambdas here, eigenvalues here. And then similarly, you have left eigenvectors. So that is the complete matrix here, psi 1 1, psi 1 2, psi 1 3, psi 1 4. And now how we calculate the participation factor? So that is actually the product of right eigenvector to the left eigenvector. So in the complete matrix form, we write it in this way: P1, P2, P3, P4. And what is P1? It is actually nothing but the product of first right eigenvector to the first left eigenvector here. And thus, in the complete participation factor matrix, on the row wise, we have the state variable, and on the column wise, we have the eigenvalues represented here. So thus, these are the column vectors for the eigenvalues, and these are the row vectors for the state variables. And thus, we obtain P11 here. With this, I again illustrate here. So with this here, what you have P1 here, right? So I want to discuss how we obtain P1. So P1 is nothing but P11, 21, 31, 41, right? And that is the product of right and the left eigenvectors. So we have it, this one represented here. And then we have it this part, this one, right, written here. So these are the products here, and that gives you P1 here. Similarly, when you have to obtain P2, so you will get it as from this one, this will get it, this eigenvectors, and then you get it from second row. So this is second column, and then you get it from second row here, and that gives you this part here, right? And when you have to obtain P3, so you will have to get it from this one, that means the third, and then here you have it from this one, so it will be this one here, right? And when you have to obtain P4, then it will be as the last one from the matrix, and then the row, the last row from the matrix here, and that will, so that completes the participation factor matrix here. So with this, I will end here, and then I will discuss more with examples on small signal stability analysis in the later on.